Okay, we need to talk about toys, and toys in terms of laboratory toys. And the toys that we're going to talk about is refractometers. So refractometers can come in many forms and many shapes and many sizes. It just depends on how much you want to spend on those toys. So this is one of the first. These are the cheapest of the cheap. They are sold on Amazon probably all the time, and they're pretty skanky and nasty. They do a pretty good job, don't get me wrong, for aquarium prep and saline and salt solution type of stuff. There's not an issue with them at all, but these are not what we would call laboratory standard, nor are they USPNF approved. So you can get a hold of these every day, all day, use them, not a problem, whatever, but we will never use something like this in a laboratory. So great for starters, great for at-home use, but really not for a laboratory setting at all. Next is the Abbey. This is what we call the OG. Now, this is not termed the Abbey refractometer, but they look very similar. So this is the most common brand, the Abbey model is, and it looks very similar to this. So here in the front, this is where you're going to see the sodium D bulb. So the sodium D bulb is right here. When this machine turns on, this bulb glows, that traditional orange color from a sodium lamp, and that light energy gets directed into the prism that is right here. That means that this top piece opens up and it's on a hinge. So you'll put a few drops of your sample material on that prism, and then you'll close that top piece back, and then you'll raise the bulb up and you turn it on. So that is the proper process of how to get a sample loaded up on these things. Over here to the right-hand side, like ours, that we have in the Chemtech lab space, we have some thermometers. And this thermometer will allow us to get a temperature readout of the sample or the sample compartment. This model also has a piece of plastic tubing that comes from the back end, it looks like. It goes by the thermometer, and it looks like it goes up into here, and then it circulates back again and around on the other side. This is a flow cell type of model, which means that there is probably some type of liquid like water. That water is getting heated to a certain temperature, 30, 35, 40, 25, whatever the case is. And that constant flow of that temperature regulated water will control the temperature of the sample cell. So when I heat the water up, that's going to heat the sample cell up, and therefore I can take a reading at that appropriate temperature. So those are the flow cell models that were used probably very briefly back in the day. Here's another model of a refractometer. Same kind of style, same kind of setup, except here we have a digital thermometer readout and not an actual thermometer. So once again, I see a few dials, probably one to raise the dark half up and down, and then probably another one that is specifically for the fine focus. And then this one has one eyepiece that I'll look through that's probably going to give me the crosshairs, and then I flip a switch, and then that's probably going to give me the scale or the meter that I need to read in order to record my values. Here's another version of a refractometer. Again, same basic concept as here. I see a sodium D bulb, and the bulb is going to be directed into a prism. This prism is going to open up and close so I can put my sample on the inside. And then this one clearly shows kind of the temperature regulator. So I've got this kind of fluid that I'm pumping through the machine, and I'm setting the temperature on there so that way the sample compartment can be heated or cooled appropriately. And when I put my sample there, I'll give it a few minutes to equilibrate, and then I'll take my reading as far as refractive index goes. Over time, these have quickly been replaced, and it's because of the meter. As you can imagine, one person can go in and read the meter, another person can go in and read the meter, and they will report back two different numbers. And I don't want that for repeatability, and I don't want that for accuracy either. There is a mistake that can happen, And part of quality control is to make sure that those mistakes do not happen. So if we can automate this process and make it a little bit easier and take the guesswork out of it, then all of a sudden our job is going to be much easier. So this is what I would call more kind of run-of-the-mill, commonplace refractometer nowadays. The same concept is here, except I just don't read a meter anymore. I just read out the number that it tells me. So the instrument is going to do the readouts. The instrument will make that determination, and it will pop the number out onto the computer screen for me, so that way I can print it, or that way I can record what that value is. Same kind of concept though. There is a temperature regulator on here, so I set the temperature of what it needs to be, and then I open the door up, and when I open this door up, I'll place a few drops of material on the top, and I close the door back down. So that way I get a proper reading of that material. So whatever the number shows up, that's what I write down on my report, and I call it a day. It makes refractometer and the use of a refractometer so much easier than what it was before, with all the guesswork, especially on how to read that scale, which it seems like a lot of people had trouble doing. Here's another image of the more modern kind of state-of-the-art refractometer. This one's from Rudolph Research. This one, of course, was Mettler Toledo. But here's a Rudolph Research one. And the Rudolph Research, same concept. This door opens up. I'll place a few drops of liquid solution onto that prism, and I close that lid back. That way it prevents evaporation. It stays there, whatever the case is. Over here to the right-hand side, it's a big computer screen that's touch screen. And then I go in and make my temperature settings. I can name it, tell it how I want to print the report off, blah, 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 blah. And then the number will be displayed on the screen for me after that measurement is complete. Okay. We do not have a Rudolph Research at the moment refractometer. What we have are Mettler Toledo refractometers. Ours look a little bit different because we have the cheaper version, but very similar to what you're seeing here for their R5 model. And then finally, we got like full-blown automation on these refractometers. So this is just an Anton Par refractometer. And what you're seeing here is an auto sampler that's to the left. And this auto sampler is going to be a way that we can load up multiple different samples at a time and key them in, fill out a batch table, tell the machine what's there, and tell the machine how I want those samples named. And the machine just takes over from that moment on. So there's a needle that's here, and that will suck the sample up into the chamber, and that chamber will read that refractive index, and it disposes of that sample, and then it moves on to the next one. And it just does this over and over and over and over. Of course, it has to clean. Of course, it's got to kind of prep the sample compartments in between the sample runs. But this is a way that I can run multiple samples at a time and not really be there with it at all throughout the course of the run. So very convenient, very nice, way expensive. But for some labs that do refractive index all the time like this, of course they would go for an auto sampler that will make their life much easier because of that. Finally, what I want to talk about is validation. And validation is the concept of validating to make sure that the machine is working the proper way, right? That's what this is. So we are verifying the refractive index instrument. And before I do these readouts and before I use the machines, probably on my quality control form, I'm going to be writing in refractive index values. And then they're going to give me maybe some reference standards that I need to run as well. And if the reference standard matches textbook, then that means that my samples are probably really close to what proper readings are supposed to be. So it's just a quality control sample that gets thrown in. And I can also use this reference standard, just run of the mill on a random day, just run the standard, and hopefully I get the appropriate number. And that allows me to kind of keep check on the status of the equipment. Is it going out of line, or is it still reporting accurate numbers like it should be? So in order to validate, what I use is water. Aha! Yay, water! So it's pretty cheap, right? Nah, no, it's not cheap. So this is standardized water. It is super pure water that they will sell to you in a tiny little bottle, and these bottles can be hundreds of dollars. You get multiple uses out of it, but the reference standard does have to be replenished or exchanged after so many, number of months that you've had it, or so many uses that you've had it. So notice this little bottle is 30 milliliters on the label. And that 30 milliliters would be enough to do multiple standard runs without a problem at all. But there is an expiration date on it, and I want to make sure that that expiration date has not passed when I go and start running and analyzing and operating these refractometers to make sure they're still in line. So what's the deal with water? Well, number one, water's very easy to get, very easy to purify, and it is a standard that's used in many, many different things, not just refractometer, but in many other things as well. So we kind of know how this is going to operate, and there are some numbers here that I want to go by and that I want to remember when I do this in a real lab environment. So the accuracy of my refractometer here should be plus or minus 0.0001. So that means when I get a reference material like water, then I should put that reference material on the refractometer, and I should get a value that is plus or minus 0.0001 of that. So keep in mind, I told you that refractive index is a fingerprint to many compounds. We can use that to identify things that are out there. This is no different, but this also shows you how tight the numbers need to be. So when I take this distilled water and I place a few drops on the refractometer and I do a measurement, if I do the measurement at 20 degrees, then I need a 1.3330 readout, plus or minus 0.0001, right? And then if I increase the temperature to 25, my temperature readouts need to go to 1.3325. So as you can see, the temperature 5-degree difference does make a difference in the refractive index readouts, and that's very important. So double check your temperatures, make sure the systems are setting the temperatures the appropriate way, and then run standard references so that way you can run these standards and prove that your machine is operating as expected, and then you're cleared and you can turn loose to run your samples with quality control samples scattered throughout the time as well within your batches. All right. So with that said, this is really the process of how we validate. We do both temperature readouts. We like to check the 20. We like to check the 25. The USPNF really refers to 25 more. So the 25 is going to be more important than the 20 according to them. But we still like to double check both, just to make sure that the instrument is heating up and cooling down according to plan, and that my numbers are matching at both temperature readouts. So that's it of refractometer and refractive index. It's all about this incoming light, and it's all about the angle at which this light basically bends. That's really what we're after here, and that's refractive index. All liquid material will bend stuff in a slightly different way, and that is the angle or the value that you are reporting when you look through that eyepiece and you jot down these numbers. You are jotting down the refractive index value of that material. So different versions of the instruments are out there. Again, we've got the Mettler-Toledo refractometers, and that's what you'll be using when you do some of the testing that's in our program using the more automated instrumentation. All right. So if you got questions, you know how to find me. Otherwise, good luck on refractive index. Notice we didn't go through correction equations. We didn't go through any kind of math. We didn't do Snell's law or Snell's equation. And I just don't think that it's needed for our purpose. It's out there. It's something that can be talked about. Great. Whoop-de-doo, whatever, but not here. So it's more just lecture, what is it, theory behind it, and some of the instrumentation that we use to make our job a little bit easier. So keep in mind, USPNF is going to be 831 refractive index. You'll have that document, you'll have that reference to go by, so make sure that you kind of understand the purpose of why we use them, for major reasons that the USPNF really tells you about, and what is the abbreviation that we use for refractive index. So the N with the temperature at the top, and then down below is the wavelength, and that will be 589 every single time, or D, and that means the same thing. Sodium D is 589 nanometers. Okay, so good luck on the online assignment. I'm here if you need me, but you probably don't, and that's fine too. Whatever. I'll see you in the next video series.